Alright, so in this video we'll be covering some log rules. So this is part 2 to a previous video made covering logarithms and what they are, as well as how they relate to exponents. So essentially an introduction to logarithms. So this video serves to introduce you to log rules. So let's take a look, starting with the first rule. So the very first rule is simply notational, and it relates to what's known as the natural logarithm, written as ln. So ln actually secretly means log base e. So this is what ln actually means. So if you see anything with ln, such as ln of e, what this really means is log e of e, which of course we know to be 1, since e to power 1 equals e. Another example problem that we could do is just ln of 1, which again is log base e, and then of 1. And we know this to be 0 because any number to the power 0 is 1. Now, to clarify what e is, in case you haven't encountered it before, e is a special number that appears in calculus. It's approximately 2.71, etc., etc. And it's a special number. Consider it similar to pi. So you know how pi is equal to 3.14 and goes on forever. So e is similar but serves a slightly different purpose. And you'll see it appear in places such as calculus, pre-calculus, differential equations. So it is ln is a surprisingly useful function, but essentially this is a notational rule. Alright, so a slightly different rule, what's known as the product rule. So the product rule states if you have a logarithm, such as log a of b, and we add log a of c, this is going to be equal to log base a of b times c. And we can demonstrate this with this rule with an example problem again. So for instance, let's take log 2 of 4 plus log 2 of 2. So according to this rule, this is going to be equal to log 2, again keeping that base, which you can see is denoted a here. So we're keeping the base and we're taking essentially the arguments of the logs and we're multiplying them inside this new log. So we're given 4 times 2, which is equal to log 2 of 8. And we can actually verify that this rule holds for this example. Log 2 of 4 is 2, since 2 to the power 2 equals 4. Similarly here, log 2 of 2 is just 1. And on this side, and there's a plus sign here by the way, on this side here we have log 2 of 8, which we know to be 3. So what this is saying is 2 plus 1 equals 3, which again we know to be true. So that's essentially verifying this. And we can actually derive this rule using simple exponent rules. And let's very quickly do that, essentially to demonstrate how this rule really works. So for instance, suppose we were to raise both sides of this equation to the power a, to the a power. So we have a to the power of both sides of this equation. And we need to both sides so that remains an equation. So we have log a of b plus log a of c in the exponent over here. And on the right side, we have a to the power log a of b times c. Now, remember from last video, the logarithm is essentially the inverse of exponentiation. So when you have the same base here, these logarithms essentially cancel out. So you can see that on this side, a and log a cancel, and you're left with b times c. And on the left side, remember when we have a sum inside an exponent, that really translates to multiplication. So this turns into a of log a of b plus a to the power, or rather times, so let's do times, a to the power log a of c. Again, the a's and log a's cancel, and you can see where this is going. So b times c equals b times c, which is self-evident. So this effectively proves this above theorem. So a very similar theorem that follows from this one, or rather rule for logarithms, is the quotient rule. So instead of 3, actually, I'll denote this 2 part I, and this one up here can be 2 part I. So this one will be called 2 part I just because it follows very similarly. So essentially it says if we have log a of, say, b, and we subtract log a of c from it, this is going to be equal to log a of b divided by c. So essentially, you can see that this is the reciprocal. This multiplies by the reciprocal. So what I mean by that is this is very similar to the product rule in that if we did log a of b plus 1 over log a of c, or sorry, rather log a of 1 over c. So that would yield log a of b out of c by the product rule. So putting this together, you can see another part that follows from this, and let's call this rule 3, is what's known as the reciprocal rule, which is that negative log a of b is going to be equal to log a of 1 out of b. And again, these can be shown very simply through exponentiation, similar to what we had up here. So we have negative log a of b equals log a of 1 over b. And what we can do in order to demonstrate this sort of is another example. So let's take log 3 of, say, 47, doesn't really matter, minus log, let's say log 3 of 56. So what we're going to do is use this rule in conjunction with this rule up here. So this rule up here. So what we're going to get is essentially log 3 of 47 plus log 3 of 1 out of 56. So that again derives from this. And from here we can just use the product rule. So log 3 of 47 over 56 is what we get because we're multiplying these the insides, or rather the arguments of both of these logarithms. And that falls from the product rule up here. So yep, up here. All right. So now let's move on to another rule, yet another rule, and that is going to be essentially a division rule between, it's a different type division than the quotient rule, and you'll see why. So this goes something like this: log a of b divided by log a of c is equal to log c of b. So you can see these arguments in themselves develop these, or sorry, that is supposed to be c. So let's make that c. Alright, so you can see these arguments sort of became the base and the argument of the log in and of itself. And this is actually very good as a trick in case your character, say, only has log 10. So log 10 is commonly assumed, so this is another notational thing. When just log is written with no base, most often it's assumed that this represents log 10. Implicitly, there's a 10 down here. In very few cases, this might also implicitly just writing log with no base. In a few contexts, can also just represent the natural logarithm, which is again represented ln, which, if you remember, is log base e. So sometimes it's implicitly e, sometimes it's implicitly 10, but for the most part it's 10. And if you see it on your calculator, it's most likely a 10. It's most likely representing log 10. So given that you have only log 10 in your calculator, how can you find, say, log 4 of 7? So if you want, pause the video here for a second and try and solve this question. Alright, so I hope you got a chance to think about this for a bit, but essentially what we can do is use this rule up here, which you probably guessed, and we can take of uh, log of 7 and divide by log of 4, and by the above rule up here, we're going to get log 4 of 7. Alright, so you can see that this is very handy, especially if your calculator only really has log 10. For instance, you can calculate any logarithm you really want. Alright, another logarithm rule that we're going to cover is what's known as the chain rule. So this is rule 5, I believe? Yes, 5. So the chain rule goes something like this. Log a of b times log a of, log c of d is equal to log uh, log a of d times log c of b. And essentially you can see I can just flip these arguments around, even if they're in a chain, and it works quite well. And this can be proven very simply using this rule above. So this rule up here we can use in order to prove this, because we can rewrite log a of b as, say, log uh, log b over log a. Similarly, we can write log c of d as log d over log c. And again, here I'm implicitly assuming when I write just log that there's base 10 here, although it doesn't really matter. So what we're essentially doing when we multiply log a of b by log c of d is we're multiplying them. So if we multiply these two, you can see that this we can just rearrange by the commutative property of multiplication. We can just rearrange the numerators, and we have log d over log a times log b over log c. And oops, sorry, these are the arguments and not the bases, so I will clarify that. So you can essentially see once we simplify these back down using that rule, we get log d base a times log b base c. So essentially we have proven that this rule holds using another rule that we learned about. Alright, one last rule that you should know about. It goes something like this. So this is rule 6, I believe. Is this rule 6? Yes, this is rule 6. And it goes log of log base a of a to the power, say, x is going to be equal to x times log uh, a of, I suppose, a. So I should make this argument b to really demonstrate this rule. So this is log a of b to the power x is going to be equal to x times log a of b. And again, this is one of those theorems that can be demonstrated quite simply with exponent rules, but we won't derive it here. But we can do a practice problem. For instance, suppose we have log, let's say 9 of 1/3 to the power 300. Now, you don't really want to have to calculate 3 to the power 300 for that denominator here. And let me just clarify that this is a 3. So what we can do is you can turn this into 300 log 9 of 1/3. However, we can actually go a step further. We can resolve what log 9 of 1/3 is. So we can actually write this 1/3 as 3 to the power -1, and we can write this as log 3 squared of 3 to the power -1, and this is 300. So this is actually going to be equal to -1/2 because 3 squared to the power negative a half equals 3 to the power negative 1. And we're given 300 times this negative half, which equals to negative 150. So this is in essence can be a very useful rule on your math problems to simplify these massive equations quickly. All right, and there's actually one more rule, and it goes something like this. You have log a of b, and suppose we want to switch b and a, and we can actually do that. This is equal to 1 over log b of a. And this again is particularly useful because you are no longer stuck with just using a as your base. So we can do another example problem here. Suppose we want to multiply log 3 of 100 times log 5 of 10. Or sorry, let's do log 10 of 5. Let's do something like that, I think. Should be good. So we can actually rewrite this as 1 over log 100 of 3, and multiplying this by this log 10 of 5. So log 10 of 5. What you're going to get is log 10 of 5 over log 100 of 3. And this is particularly useful is because this 100 and 10, they're essentially powers of one another, right? So this is essentially 10 squared. So if this is 10 squared, we should be able to turn it into log 10 of something. Log 10 of something, yep. So this can actually be written as, and let's see. So this can be written as log 100 of 3. So what's going on here is that when you take log 100 of something, well, this is just 10 to the power 2, right? So this is log 10 of the same thing, so 3, except what we're doing is that we're dividing it by 2. And I can give a very simple example for why this is the case. So suppose we have log 100 of 100,000, and we have log 10 of 100,000. So this is equal to 4, this is equal to 2, and you can see that it's half of this. And this is essentially whatever power 10 was raised to is the factor that you're getting rid of down here. And we'll put that in as another rule. So what you're going to get is log 10 of 5 over log 10 of 3, and then divided by 2, but that goes up into the numerator here. So this was divided by 2, but because you're dividing twice essentially, this is in the denominator of the fraction, the 2 goes up to the numerator. And we actually know how log 10 of 5 over log 10 of 3 can actually simplify further. We can get 2 log, so this 2 is from over here. And so you get log 2 of 3, so log base 3 of 5. So it essentially can simplify down to that. Alright, so as promised, one last rule to show what I demonstrated here. And this is going to be rule 8, I believe. Yes, so rule 8. And essentially if log, and then in the base, we're going to write a to the power b of c. This is going to be equal to log, let's say log a of c divided by b. And again, this was demonstrated with an example up here, so we do have an example to go with that. Alright, so this should be a pretty comprehensive list, so let's just go over a recap of all of these rules again. So yep, that's two-part. Okay. So the first one, of course, is that ln, the natural log, is it's written this way, ln, and it's implicitly just log base e. The second rule is the product rule. If you add two logarithms with the same base, their arguments will multiply. You can multiply their arguments and keep the base. And then quotient rule is very similar, except that if you're subtracting, you divide the arguments and keep the base. Alright, and then over here, essentially we have, if you take the negative of any given logarithm, then the base remains, but you take the reciprocal of the argument. So that is going to be equivalent. This rule essentially shows is that if you divide two logarithms with the same base, their arguments become the base and argument of the logarithm it is equal to. So you can see this becomes log c of b. Then over here we have log a of b times log c of d, and you can always switch the arguments around whenever you multiply two logarithms. So this is essentially a chain rule. And as you explore further problems, you'll realize why it's called that. And then here we have the sixth rule, and essentially gives us that if you take the logarithm of something raised to a power, that power drops down as being multiplied by the logarithm of just this base times the base of the exponent, whatever was raised to the power. Then finally we have this rule. If you have log a of b, you can invert the argument and the base by taking the reciprocal. And then finally, very finally, we have this rule, which is log of anything raised to a power of an argument is equal to that anything as still as the base uh, of whatever the argument was divided by whatever power it was raised to. Alright, so that should be essentially all of the logarithm rules that you need to know. And yeah, I hope that this was helpful to you. And yeah, so thank you for watching, and consider subscribing. And yeah, see you in the next video.